Okay, so the plan for today is to finish chapter 8. I think we ended up talking about cis dihydroxylation. The most common reagent by far used for that is osmium 8 oxide or osmium tetroxide. In pyridine solvent, we need a pretty polar solvent here because there's some very polar intermediates that we need to be able to dissolve. So, and I went over the structure of pyridine also the last time. There then is a second step. We usually call this the workup step, which means that we're going to, and we'll talk more about this later too, but it means that we're going to destroy any leftover excess nasty stuff so that we can more easily isolate our compound. One nice rule to remember about workup steps is you want to add the chemical opposite of whatever you're using in the reaction. And so here we're using a very strong oxidizing agent, so we want our workup to be a reducing agent. Maybe if maybe our reaction had a strong acid present, then likely we'd want the workup step to be something alkaline to neutralize the acid. So that's just an example. You want to add the chemical opposite in order to get that to work. The product will be the cis 1,2 diol of this type. And in this particular case, again, we actually have a meso compound. So if you'd drawn it with the bonds dotted, it happens to be the same thing. So, but you will get, I would expect only that compound. I would not expect either of the trans diastereomers, only the cis compound. There is an alternate reagent that your book mentions. Potassium permanganate does the same thing. You're not responsible for that mechanism either, but it's good to have two sets of reagents that do the same thing in real life, because what will generally happen, almost always, is you'll try something and it won't work. It's actually very rare for something to work the first time you try it. So it's nice to have an alternate reagent that will do the same thing. So potassium permanganate, the permanganate ion is just about the strongest oxidizing agent known to man. It pretty much oxidizes anything. So that will do the same thing. And you'll get a chance on OWL to see what sort of things you might get asked. That will give you an idea of where potassium permanganate comes in. I should also mention, sometimes OWL has you practice mechanisms even though you're not going to have to know them for the exam. That sometimes does happen. And so I think there's some utility in that too, even if you won't still have to know it for the exam. Good, and then I think we ended class last time introducing the idea of the ozonolysis reaction. This is actually another addition reaction to alkenes, just like the osmium reaction is. Both of them involve adding something across the alkene pi bond. And ozonolysis, like osmium tetroxide reaction, is an oxidation reaction. And it does involve the ozone molecule adding across the alkene pi bond. It then undergoes a couple of rearrangements. It's kind of a pain, but I'm not going to ask you guys to learn the mechanism. And the reason that you're not responsible for this mechanism is because, to my mind, there's no academic benefit for you, either for my teaching you the mechanism or for your learning it. I see no value in it. And the reason is this particular mechanism is the only one of its kind that we will ever see. Happens to be called a 1,3 dipolar cycloaddition, in case you're curious. But it's the only one that we'll ever see, either this term or next term. So I don't see any benefit in you guys learning it. And they do make a pretty good effort at it in the textbook. That's probably about the best you can do. But even though you won't have to know the mechanism, you still need to know how to predict the product. And I will have a nice little shortcut for you in just a few moments. But the products that you get are cleavage products. You wind up with two carbonyl groups where you had the carbon-carbon pi bond. So in order to figure out what the product is, here we go. Here's your shortcut. You find the alkene pi bond, and then I want you to take your scissors and cut the pi bond right down the middle. And when you're done with that, I want you to take your oxygen tweezers. You should have been issued a set of oxygen tweezers with your textbook. I should, because there's always someone. Really? Because I didn't get any oxygen tweezers. There's always someone. So I'm just using figurative speech here. Anyway, I then want you to take your oxygen tweezers and put an oxygen on both formerly alkene carbons, and then you're done. So you will actually get 2 molecules if this is an acyclic alkene. But if the alkene is cyclic, you can actually wind up with just 1 molecule, just where that double bond has been cleaved. And we'll do examples of both of them. Let's see. Left mine at home, my what? Well, anyway, they're having a discussion in there, and that's fine. Good. So my old friend and now colleague Jim Pennington does this a little bit differently with his students. You see, I'm a peaceful man, but he's much more violent. What he tells his students is, I want you to take an axe and chop that double bond and then cap the 2 bloody stumps with oxygens. You know, so if you want to learn it that way, that's fine. Oh, you sold your oxygen tweezers for video. Okay. Probably got a fair bit of money for it. Anyways, I didn't even get it. I was a little slow in the uptake. Good, so either way you get the same thing. So for instance, if we took, let's just make up an alkene, maybe something like this, let's at least leave 1 hydrogen on there. We'll take that one. And we treated this with ozone, or I should mention there's again another set of reagents that does the same thing, periodic acid and aqueous THF. We'll do the same thing, scissors plus oxygen tweezers. I had a colleague at my former school that the oxygen tweezers just drove her insane because people would be mentioning that when they had her for biochemistry. And I said, sorry, not sorry, because it works. Oh, anyway, I should also mention, this doesn't have to be acetic acid. I've also, you can also put HCl. Either of the 2 will work. You'll probably see, but there are other reducing agents also that you'll probably learn about in the OWL assignment. So basically it needs zinc and aqueous acid, but I should mention that's a very good reducing agent. Metals in general, and again, please notice that's metallic zinc. That's the pure element, not the ion. But metals are very good reducing agents because they really, really want to give up electrons and make cations. This really wants to be the zinc plus 2 cation. So it gives up 2 electrons in order to do that. That's also known as being a reducing agent, because if zinc gets oxidized by losing 2 electrons, if it gets oxidized, then it's the reducing agent. It reduces something else. Terrible term. I've taught Gen Chem enough, as I said. We always struggled with oxidizing agent and reducing agents. Strange term, because if you're an oxidizing agent, you aren't oxidized, or yourself, you're reduced. You oxidize something else. If you're a reducing agent, you aren't yourself reduced. Yourself gets oxidized, but you reduce something else. So same thing here. So metals are very good reducing agents. Anyway, in the end, we will take our scissors and cut that double bond. Well, I guess I already had a hydrogen on there. Well, maybe I'll put that methyl group back then. And so over here, we will get an aldehyde functional group, since there's the hydrogen over there. And the other piece will be this ketone. And of course, there's many correct ways to draw it. We can call that guy 1, 2, 3, 4, 5. How about 2-pentanone? Seems legit. We'll learn how to name ketones next term. But I would expect you would get both of those products. And that's typical when the alkene is acyclic. What though if you had a cyclic alkene? Like, oh, I don't know, cyclohexene. I'm just going to, well, no, I won't. I'll write it out. Ozone, dichloromethane. Dichloromethane is a very good solvent choice. It's quite inert. It doesn't react even with ozone. And we're going to wait until it's done reacting and then add our zinc and aqueous acid. Be ready also, there's a lot of different ways to write acetic acid. So you have to be flexible. But again, we're going to cut the double bond. And I want to get this right. There's 4 CH2s. There's my 4 CH2s. And we'll have aldehydes at both ends. So these 2 carbons become the 2 aldehyde carbons. And I just want to double check, since I got this wrong in my other class. Yeah, there should be 6 carbons total. So, yes, please do be aware that CHO is an abbreviation for the aldehyde group. Remember the rules for this kind of thing. You never have to use these abbreviations if you don't want to. It's completely optional. If you would rather write out the aldehyde group like that, that's fine. You never have to use these abbreviations like this, or CO2H for carboxylic acid, or ET for ethyl group, right? PH for phenyl group. It's always optional to use the abbreviations. I only ask that when you see them, you understand them and have an idea of what the structure actually is. So I would expect that you'd get this compound as a result. And that's very typical for a cyclic alkene. Maybe one more. Oh, I know, let's go crazy. I would be willing to bet a fairly large sum that you'll get one of these in OWL too, that they'll give you some kind of bicyclic compound like this. And it's good for you to be comfortable with structures like this, because we'll get to them, I think, already in chapter 10, coming up pretty soon. At least I think so. Good, so what if we treated this with ozone? Or periodic acid in aqueous THF, you'd get the same thing. Zinc, water, and either HCl or acetic acid, doesn't matter. Well, let's think about what we're going to get. These 2 alkene carbons are attached to opposite sides of a 6-membered ring, aren't they? So, I mean, you can certainly draw it like this. CHO, that's fine. There's nothing wrong with that. But you can also draw it. Can you see the 6-membered ring here? 1, 2, 3, 4, 5, 6. And so it's carbons 1 and 4 that the 2 aldehyde groups will be attached to. So you can also do it like this. That's also an acceptable way to write it. Same compound. But I'd like you to be comfortable with both. I don't want you to think of either of those as better or safer. They are equally correct, exactly equally correct. So but this is actually as good a place as any to bring up this idea. What do you need to do in order that you know what you have to know for the next exam? Well, I've given you in your chapter 8 class notes a method that you can use to learn reactions. And it's not the only way to do it, but it's easily adaptable to any given reaction. It's what I recommended to my students at my previous school who found it helpful. Students here so far have said they found it helpful also. And for what it's worth, it's what I did when I was in college. And I did pretty well in organic chemistry. Better have, in order to have become a teacher of it. So what it all starts with, since all of these reactions involve alkenes, it starts with making up an alkene. And so that's a skill that you're going to need to develop. Don't just wait always to be given something, although you certainly will be, whether by me or by OWL. Learn to make up a starting material. And so it's going to be an alkene. Okay, fine. There's my double bond. And then pick a number of carbons. I want my alkene to have 7 carbons. All right, so 1, 2, 3, 4, 5. 6, 7. I'm just going to make something up. And so then pick a reaction to practice. Maybe now we're working on ozonolysis, or you could take the aqueous THF periodic acid. But let's pick these reagents. If I were you, I'd have a bunch of slips of paper with all these different reagents that we're learning. And whether in a literal hat or a
proverbial hat, pick them out of a hat each time. Make up an alkene and pick something out of a hat. If it's a reaction that you need to know the mechanism, then work through the mechanism and figure out what the product looks like. I would do that again and again and again and again and again. It's impossible to overdo that, I think. And I believe that will help you to get where you need to be for the next exam. And it's what I would recommend for every chapter that's like chapter 8, and there will be many more like them, where you have to learn a bunch of reactions. So in this case, we take our scissors, we cut our double bond, and we use our oxygen tweezers to put oxygens on the ends. I should let you know, or maybe I shouldn't. My old friend and colleague, now colleague, Dr. Jim Pennington, see, I'm a peaceful man. He's much more violent than I am. What he tells his students, and they will probably tell you this when you ask them, he says that you take an axe and you chop the double bond, and then you cap the bloody stumps with oxygens. You can use that too if you like. I don't want to go that far. I have a weak stomach. I'd rather we just cut the double bond with our scissors and then used our oxygen tweezers to put on oxygen. So I would expect to get these two products. Or, make up something else that's cyclic. I don't know. What about that one? Well, same thing. I'm just going to do dittos over here. Same thing. Well, I want to make this right now. We have 3 CH2s. So all 3 of those carbons are CH2s. Well, all 3 of these carbons are. This carbon is going to have double bond O and a hydrogen. In other words, it's going to be an aldehyde group. And this carbon over here is going to have a carbonyl and an isopropyl group. Let me just make sure that's right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, that looks right. So I think that's going to be the product. And then maybe pick a different reaction. Figure out what happens if you treat this with peracetic acid or with chlorine and water, and keep going. If it's one you need to know the mechanism of, and I think I'm pretty clear in the class notes as to whether you do or do not have to know the mechanism of any given reaction, then work out the mechanism and figure out the product also. I can't think of anything better to recommend that you guys do in order to practice for the next exam, or with any chapter that you have to learn a bunch of reactions. Good, I think that's all I really need to say about ozonolysis. Let me see, we have now 2 flavors of cyclopropanation, and then I think we will finally be done. Students ask me about this chapter. Dr. Wass, do you know how many reactions are in this chapter that we'll have to learn? No, I've never counted. Students do sometimes. I don't know that that's a useful thing to be aware of. I don't know if it's really relevant. It's up to you, I suppose. But no, I will confess I've never counted. Good. Any questions either in person or in chat about ozonolysis of alkenes? Nothing in chat, nothing in here. All right, well then, let's cover cyclopropanation, when we're also going to meet another kind of reactive intermediate. Cyclopropanation of alkenes. There actually is a way to add a carbon across an alkene pi bond. And there's 2 different types of reactions that we can do. One of them gives a Ch2 group up here. We'll learn that one second. And the other one, there's 2 different reactions. The other one, which we're going to learn first, gives actually a dihalogenated carbon up here. CX2. And so X is going to be what? I think it's going to be basically chlorine, bromine, or iodine. I don't recall if fluorine works. My tendency is not to trust fluorine, but I know that you can make CCl2, CDR2, and CI2 for sure. CF2 maybe, but I would be hesitant. Good, so these are the two reactions we're going to learn. I think you'll agree that both of those products are cyclopropanes. So they're, once again, very strained rings. One bit of advice I can give you guys, please do not confuse cyclopropanes with epoxides. They are completely different critters. They're both very strained, of course, both of three-membered rings, but they are not the same thing. Don't confuse epoxides with cyclopropanes. They're different animals. Good, so the first one we're going to learn in particular is how to make a dihalocyclopropane. And those reagents are chloroform, bromoform, or iodoform in the presence of aqueous base. And in that case, you will get again, the dihalogenated compound. CCl2, CBr2, or Ci2. And there are inorganic side products as well. I would expect that you would get a water molecule and another halide ion, I suppose. But the major organic product will be this dihalocyclopropane. So to give an example, let's start with my favorite alkene. And let's treat this with chloroform in the presence of aqueous base. And again, be flexible. It may say OH minus, it may say NaOH, it may say KOH. There's lots of different ways of writing this. And I would expect with stereochemistry that what we would get, actually let me, would look something like this, plus it's an enantiomer. So you would get both. Correct ways of drawing the enantiomer include changing the methyl to a wedge bond and the two carbon-carbon bonds to dotted bonds, or you can just draw the mirror image. You know, move the downwards methyl over here, move the three-membered ring over here. There are other correct ways to draw the mirror image also, and you'll know what you need to put based on how the question's phrased. OWL will sometimes say draw all possible stereoisomers, in which you'll have to draw both. Once in a while, it will say, don't even worry about stereochemistry, in which case you can just use straight lines. And you can check my old exams to see what I usually do. Normally, if you get a racemic mixture, I only want you to draw one enantiomer. I think it's pretty clear the way I phrased it in my old exams. I don't plan to change that radically for you guys. Good, but you'll know what to put based on what you're given in the question. So what is the mechanism of this thing? The mechanism is known, and it goes through an intriguing kind of electron-poor carbon known as a carbene. And carbenes are funny critters. They're carbons with two bonds and one lone pair. And they are funny creatures, but this is a thing. And of course, the two bonds can be to anything really. Alkyls, hydrogens, halogens is what it's going to be for us. And if you work it out, if you use that equation for formal charge on a carbon with two bonds and one lone pair, you'll find it has a formal charge of 0. Strange but true. So, so I would recommend you check that out if you'd like to convince yourselves of that. But it's a strange creature. It is a neutral electron deficient carbon. And this reaction goes through that kind of intermediate. And I do believe we'll run into 1 or 2 more carbenes down the road. So I think it is worth us seeing it here. Good, so the way this reaction works is we're going to start with our haloform. And again, I could just as easily have used bromoform or iodoform as chloroform. And what happens is our base is going to pull off the one and only proton on that haloform. Now, normally carbon-hydrogen bonds aren't all that acidic. However, in this case, the carbon atom bears 3 electronegative halogen groups. And again, don't refuse to learn these things that I'm telling you, these things like what I'm telling you here. It's what's going to help you to know the reaction properly. It's what's going to enable you to understand it at a deep enough level that you're able to apply the material no matter what the starting material is that you're given. This is how you will remember what you're doing when you're writing mechanisms. So because we have these three very electronegative halogen atoms sucking electron density like mad away from the carbon atom, it's not therefore that surprising that you can get a carbanion like this one. And it will have these three halogens, as I said. And so, so that's the first step. And by the way, this carbanion is known to be the intermediate. So this thing doesn't collapse to a carbene all at once. You also have this trihalomethyl carbocation as the intermediate, a carbanion, sorry. And at this point, one of these three halide ions, it doesn't matter which, since they're the same, is going to fall off. And that will get rid of the minus charge and get us to our carbene. So there's our carbene intermediate, our dihalocarbene. So again, this is known to take two reaction steps. You can't put those into the same step. This is known to take two steps going through a carbanion intermediate, and then you get your carbene. And it is the carbene that adds to, let me make that look a little better. It is the carbene then that adds to the alkene. And that mechanism looks an awful lot like, actually, let me turn that or something. That mechanism now looks an awful lot like the epoxidation mechanism, in that what's going to happen both at the same time is the lone pair on the carbene is going to add to one of the two alkene carbons, it doesn't matter which, and the pi bond is going to form a bond to the other, or from the other alkene carbon to the carbene. Or again, another way of writing this mechanistic step, if you prefer, if you like giving yourself a visual aid and using dotted lines, you can do that. You want to put dotted lines here, then you can show one arrow going between those two carbons, and then you can show the pi bond swinging in between the other alkene carbon and that carbon. I consider those two equally correct. I have no preference of either one over the other. And in fact, you could also have drawn both of these. I think, looks like I went counterclockwise. You could just as easily have gone clockwise. Not only would I not take off points, I wouldn't even notice. I'm trying to wean myself off of talking like this all the time during lecture, but I know it's helpful, at least at this level, at least until you've had a few exams under your belt. But that's an example of something that I see no difference. I think they communicate the same thing. Either way, you're going to go straight to the product at that point. And the way you'll know how to draw it is by how the question's phrased, et cetera, et cetera. But I would expect that you would get this compound plus the enantiomer. And the way you'll know what to do if you have to draw the mechanism, remember you need to account for formation of the product shown. So you'll just make sure that what you draw matches it. And we'll do other examples, don't worry. Let me go through the mechanism again in full, since I see a lot of people still copying. The reaction starts by the hydroxide, which you will be given, you'll see it in the arrow, the hydroxide reacting with the haloform. There is one proton left, so it's pretty clear which proton you're going to take off. It pulls off that proton, which is actually slightly acidic, because you get a well-stabilized carbanion. These three halogens, and they could also be bromines or iodines, and maybe even possibly fluorines, are going to pull electron density away from this anion, essentially, and help to stabilize the minus charge on that carbon. After that, you lose one of the three halogens, it doesn't matter which, they're all the same, and you lose it as a halide ion, and if you work it out, that takes away the minus charge, and you're left with a dihalocarbene. So far, so good. Or should I go over all that again? Just making sure. Just making sure I'm making sense. The carbene then adds to the alkene in one step. it's really not that unlike the formation of the, whatchamacallit, epoxide. It's kind of like adding that oxygen in the peroxy acid, except other things happen then too. So this is kind of a simpler mechanism. But the carbene just adds across the alkene in one step. So the valence electrons point to one carbon and the pi bond points to the valence, I would say the lone pair electrons in the carbene point to one of the two alkene carbons, it doesn't matter which, one of the two alkene carbons, it doesn't matter which, and then the pi bond forms a bond from the other alkene carbon to the carbene carbon, and you get the product all in one step. I'll say all that again. The lone pair on the carbene adds to one of the two alkene carbons. It doesn't matter which. Both, I'm sure, happen. And then the pi bond in the alkene forms a bond between the other alkene carbon and the carbene carbon, and you close your three-membered ring. And like I said, you could go, as it were, either clockwise or counterclockwise. I won't even notice, as long as the arrows are pointing in the right direction, starting and ending in the right place. And you have even at least two choices for that. Either of those, I see those as the same thing. So you use whichever is better for your learning style. But I see those as the same thing. Good, and I'd like to do at least one more example. Yes? It didn't. This is the same compound as this. All I did is turned it. So it doesn't matter how you draw it. The question was, why did the methyl group move? And it didn't. Yeah, it doesn't matter. I could just as easily have put it on the other side. I just sort of drew it in a way that I thought would make it easier to see what's going on and to draw. I didn't want to have like arrows that were 3 feet long. Good, no, that's good though. Other questions? Well, let's do another. Let's take, let's take one hexene and put a couple of methyl groups on just because. And let's treat this with iodoform and aqueous hydroxide. What would be the product? Well, I would predict the product would look like this. And that's an important skill too, is being able to draw the product whether or not it asks you for the mechanism. But I would expect you would get two compounds that you would get. This one plus the enantiomer. Now, why do I know that it's okay to just leave this as a straight line and not use another wedge bond? Well, the reason is, once again, this carbon is not chiral. So there is no stereochemistry there. So would I take off points if you made that a wedge bond? Yes, yes, I would. Because it shows me you don't really understand when you do and when you don't show stereochemistry. You can't show stereochemistry on an achiral carbon. This carbon is chiral over here. So there we need to show stereochemistry. I don't want you guys just memorizing, I better put wedges and dots all over the place. There's a reason for wedge and dot bonds, and they communicate something. And so that's what I'd like you guys to be aiming for. Good, so, but this carbon's achiral, so there's no stereochemical issue there. So I would expect that you would get just the two enantiomers. Now, going back to something like this, now we have two chiral carbons. So we need to show the stereochemistry at both. And just as always, since we're fusing a three-membered ring onto the other ring, you're only going to get the cis stereochemistry. There's two of them, but you'll only get the ones that are cis. You can't make a trans cyclopropane. Not possible. Again, if you form a bond up here, then the next door carbon over here can't reach to close the three-membered ring. It's too far away. A larger ring, like maybe a 5, 6, or 7-membered ring, then you can have a trans ring fusion. That's heard of. But 3- and 4-membered rings, no way. They're too small. So that's the sort of thing that I'd like you guys to practice, that I really would like for you to become confident in, when and how you show stereochemistry. And in a case like this, I would like you guys to be confident in leaving that as a straight line. It's an achiral carbon. There's no stereochemistry. Good, so what's the mechanism going to look like? Well, same thing. We're going to start with our iodoform. We'll pull off the proton and get our triiodomethyl anion. Looking like this, minus charge. And then one of those iodide ions is going to leave. It doesn't matter which one. They're all three the same. We'll get our diiodocarbene. And that's now going to add across our pi bond. Just want to move that. Good. Just want to have my organic starting material in a convenient place. That looks more convenient. And so I'll add the carbene lone pair to one of the two alkene carbons, it doesn't matter which, and the pi bond will be used to form a bond between the other alkene carbon and that same carbene carbon. And we'll go directly there. So it's 1, 2, 3 steps. 2 steps to the carbene, which then adds to the alkene in 1 step. And that's basically it. So make up alkenes, put reagents in a literal or figurative hat, get with your classmates, make up alkenes for each other, get with your friend, frenemy, boyfriend, girlfriend, brother, sister, aunt, uncle, mother, father, dog, cat, whatever, and have the other party make up alkenes for you. I don't know how well your dog or cat will do, but you know, they'll give you moral support. And that's the best way. Honestly, to me, that's the best way of learning this type of thing. Good, so we're at 11:14. Do have one more reaction that we're not going to learn the mechanism for. And then we'll do our brief session. I have some actual questions for you this time. Good. Make sense? My dog will run off. Yeah. Bella would basically try to tear up all of the bits with the reagents on them. Good. All right. Well, last one. It's also possible to make just a plain cyclopropane with a Ch2 group, no halogens. And the way to do that, this is sometimes called the Simmons-Smith reaction, though I don't think I really care if you, I mean, Mr. Simmons and Mr. Smith might care, but I'm much more concerned that you know the reaction. And one of the reagents is diiodomethane. And here it does have to be diiodomethane. Dichloromethane and dibromomethane are not reactive enough. And the other reagent is an alloy of zinc and copper. It can be written Zn/Cu or Zn-Cu. I've even seen Zn, Cu. Sometimes it's called zinc-copper couple, but it's a special finely divided, I think it comes as a powder, but it's a special alloy of zinc and copper that increases the reactivity of both. And what you wind up getting is the normal Ch2 cyclopropane. I don't think the mechanism's really known. I certainly don't know it, and I certainly don't expect you guys to know it either. It does act, though, as if you had, what did I just do? As if you made Ch2 carbene. I don't think you really do. I don't believe that intermediate is actually there, but it acts as if that were the reagent, and that then added across the alkene. Again, I don't believe the mechanism's known. But for example, if we took our last starting material and we treated it with diiodomethane and zinc-copper couple, I would expect we would get the corresponding cyclopropane. But no, whoops, forgot my methyls. But not with halogens, just a Ch2. And so you would get a racemic mixture of those two cyclopropanes. For the other one, if we took this alkene, treated it with diiodomethane and zinc copper couple, I predict that you would again get a racemic mixture of cyclopropanes. Maybe this time I'll make the methyl group wedged and the cyclopropane dotted. But you'd get the other enantiomer too, with the cyclopropane wedged and the methyl group dotted. So you're not responsible for the mechanism. But again, if you want to think of it, it's as if you had a CH2 carbene. You don't really. I'm pretty sure that's never been spotted as an intermediate in this reaction. It's been studied to death, trust me. But I'm pretty sure that's not actually there, but it acts as if it were. Good. Any other questions then? Wouldn't the methyl go at the bottom instead? It's the same thing. I probably should have done that just to avoid confusion, but it's the same thing. Actually, it's the enantiomer. But not only would I not have taken off points, I wouldn't even have noticed. As you see, I didn't even notice. Either way, you get this and it's an enantiomer. Good. Other questions then? Okay, I think with that, we're probably good. So we'll do our reef session if there's still time at the end. First of all, everyone, please register your attendance. But there's still time at the end. I'll just make up examples of various reactions from chapter 8. What is the name of the reaction that uses KMNO4? I don't think it has a name. It's just, it just uses potassium permanganate. So, and there are other reactions in the chapter. So I was pretty clear about what you do and do not have to know in the class notes, but there just is no time. Well, I guess there might be a little bit of time. The potassium permanganate one is the one that, as I recall, is the osmium tetroxide equivalent. So it means you know two ways of doing the same thing, and you're not responsible for either mechanism. Good. Looks like that's working. Okay, so we'll switch over to polling. And my first question for you guys. Let me get this so that at least I can see it. Good. Which of the following is the major organic product of this reaction? And so this could have been an exam question. I'm sure I've asked that exact question at least once on some past exam. So we're looking for exactly one neutral organic compound and showing stereochemistry if there is any. Looks like we're standing pat. All right. So remember, this is just one of the things that's part of what it means to know a reaction. You need to be able to predict the product given the organic starting material and the reagents. So this happens to be oxymercuration reduction, but you don't even really need to know what it's called. I know that's strange, but that's not really what to focus on. What I do expect you to know looking at this is that these are reagents that give us the Markovnikov alcohol from an alkene, only if it's a case where there could otherwise have been a carbocation rearrangement. Had we done an acid-catalyzed hydration, we don't need to worry about that possibility because there's no carbocation intermediate. As it is, I'm pretty sure that acid-catalyzed hydration will give the same product. I think you'll get a tertiary carbocation and it's not going to rearrange. So either way, I think you'll get the same thing. So you also need to know what non-Markovnikov, or rather what the Markovnikov alcohol means. It means that the OH is going to go to the more substituted carbon and the H to the less substituted carbon. So those are the sorts of things you'll need to know. If you also know that it's called oxymercuration reduction, that's great. It makes me happy. But I would, if I had to choose one or the other, if I had to choose you being able to say that this is oxymercuration reduction, but not being able to predict the product, or predicting the product correctly, but forgetting what it's called, I'll take the second thing. The second thing is much preferable to me. Good. So what does that leave us? We're looking for something with an OH over here, looks like A. So I think A is the best answer. And so did you guys. Next question, which is also my last question. Which of the following will convert an alkene to an epoxide? This is also part of what it means to know a reaction. Even without being given a compound, do you understand what a set of reagents will do to an alkene? Good. Now, all of these are reagents that we learned, but only one of them will convert an alkene to an epoxide. We just did this reagent, this set of reagents. That's oxymercuration reduction. That will give us the Markovnikov alcohol without needing to worry about even the possibility of carbocation rearrangement, since there's no carbocation. Bromine in water will give us the vicinal bromohydrin. We covered that reaction earlier. Borane THF followed by alkaline hydrogen peroxide will give us the non-Markovnikov alcohol, and not because it's an exception or a rule breaker in any way. It's a natural consequence of the mechanism. Diiodomethane and zinc we just did, or you can have zinc or zinc copper couple either way, but that will give us the cyclopropane. This is the only one that's left. That's peroxyacetic acid in dichloromethane and any peroxycarboxylic acid in dichloromethane. You could use peroxytrifluoroacetic acid, you could use MCPBA, or even peroxybenzoic acid, or even some peracid you've never seen before. Any of them will work to give us the epoxide. So I think C is the best answer. And you guys also did, by rather a lot. Good. So I think that's all we need for that. I still have 2 minutes isn't really a whole lot to do anything with. Maybe I'll just get back, maybe what I'll do is I'll get back to this idea of, someone was asking about the potassium permanganate reaction. I guess that's also really a cis dihydroxylation, isn't it? But it occurred to me in my waning 2 minutes, this is one good thing to point out. And I also see now that I was getting confused between cis hydroxylation and ozonolysis at the beginning of the lecture. But let's say that you're asked to fill in the reagents. That's another possible way you can be asked a question. And let's say you're given that cis vicinal diol. Well, that would mean there would be 2 correct answers. One of them would be what we said the other day, which is osmium tetroxide with pyridine, followed by aqueous sodium bisulfite workup, NaHSO3, and water. That would be fine. Or you could put the other set of reagents that the other student in chat asked about. It involves potassium permanganate. They are equally correct. So that's something also to be aware of. It's very possible to be asked a question that has more than one right answer, any of which would be accepted. So that does lead to that. With that, I'm out of time. Sorry I don't have your exams. I really, really hope to have them on Friday. Keep checking eCampus. As soon as I know the average, I'll post it, and probably also put up like an official exam score column. But other than that, that's it. I'll see you all on Friday.